Hey guys, it's Nick Restivo here, finally getting around to doing this video. I don't know how good it's going to be because, as I said, it's the first time I'm doing it. Before I begin, a couple of things that I know I left unanswered. These little sticks, remember, that I was showing you that make the figures. A number of people asked me what they were. They were from a company called EAI Education. As I said, it's like 80 pieces, 76 pieces, and 4 protractors that cost about, I think it was $6.99 or $7.99. Well worth the investment to get across some cool ideas. The other thing that happened was, while we were doing this, I was using greeting cards, sort of like this. But I also talked about the fact that sometimes it's better to use, here we go again, poster paper. Again, I'm having that mental fart about what it's called. In any event, so what I did was, because I felt that was a worthwhile thing to do, I took a piece of that stuff and I created a design. Remember I said to you, you could just make some sort of a design on it, or you could just make boxes and let the kids color it in. Just so you know what I did here, if you want to combine this with a computer program, I made a spreadsheet basically, and I made sure all the columns and all the rows were, I believe I did a 1/2 inch or 1/4 of an inch. Looks like a 1/2 inch to me. And then I just highlighted each box and shaded them in, so there's a little pattern there. You don't have to do it as any special pattern, but this is what I did, and this is the piece that I'm going to be using today to recreate the box. I'm going to start at the beginning of the recreation of the box because I know it was so rushed. Again, I can't apologize enough for that mess. So we're going to take this thing, and again, we tell the kids basically to turn it over on its side, and we're going to find the center of it. If you remember, I said that center is called the centroid, and basically it's the point of intersection of the 2 diagonals. So, bear with me. You could obviously fast forward from all of this, but I am going to do everything that I did there on that fateful day, fateful rush day. And again, you might want to tell the kids, once they get that center, they could balance this on the point of a pen. I don't know if I could do it in this crazy camera. I can't. In any event, once they have that, then we're going to start working with the folds. Keep in mind, for the younger kids, the folds will require an adult probably, or at least a couple of teacher aides in your room. But if you're doing it with 6th, 7th, and 8th graders, 5th graders, they could probably manage. So what we did, if you remember, was we took, and again, use the vocabulary, we took the vertex that I called home plate, and we folded it up so that that vertex touched the point of intersection of the 2 diagonals. If you want to be fancy and use the word centroid, you could certainly do that. We did that all 4 times. I also asked about what happened each time we made a fold. That is, this 4-sided figure became a 5-sided figure. And again, you could play with that and let the kids try to guess what's going to happen. So when we make the second fold at second base, we now have a hexagon because it's 6 sides. Is it a regular hexagon? The answer was no. Remember the definition of regular hexagon. We do the same thing with first base and third base. I hope I'm not getting in the way here. And very key element here again is the relationship between this square that was just formed and the square that we started with. And we talked about the fact that this square is exactly 1/2 the area of the square we started with. The visual for that is that when you flip this over and you see these 4 flaps, they create the same exact size square as that. They're congruent squares. Therefore, this one plus this one equals the entire square that we started with. Then we want to do the next fold. This one's a little bit more complicated. This is the one where the kids may need some help, because we're doing that same first fold again. In terms of vocabulary, we're taking the parallel side, or this side that was created, and folding it on top of the diagonal, which it's now parallel to. So we're going to take this, we're going to roll it up and try to keep that vertex right where it is. Mine stayed pretty well there. Again, the the great thing about this paper, which name I can't remember, is that it's a little bit thinner than a greeting card. We're going to do that 4 different times, and then we're going to look very carefully at the folds that happen. So make sure you have some nice folds there. I'm going to just do it all 4 times, and again, if this is going too slow for you, I guess you could fast forward. I have no idea what this is going to look like when it's all done. I know what the box is going to look like, I just don't know what the video is going to look like. Okay, now, here's where we stop for a little while because there's so much to discuss here. First thing I had said to you, and you might want to look at the handout that I gave you because this is all outlined a little bit better in terms of where the creases are. I don't know how well you're going to see these creases. Get the kids to tell you the area of this particular square. We start to talk about unit measures and square units rather than centimeters or inches because each kid has a different size unit, but everybody has the same area for their square. So what I try to do, and I'm going to do it right on here, is explain to the kids that this particular length or this particular box, see if I can see what I'm doing, I have very little light here, that is an area of 1 square unit. So the question that you ask the kids is, well, how many square units are in this whole square now that we have? And hopefully they will come up with 32 as the answer. Again, you're going to have to use your guide as we're going through this because I don't want this to go much longer than it has to. A couple of things to watch out for. Remind the kids that this triangle is exactly the same size as this triangle, and if you put the 2 of these together, you do get a square unit, 1 square unit. One of the other things I mentioned was if you make all of the kids' square cards the same size, they could actually put 2 of them together and see that this fits like a puzzle piece to the next one, and they're going to see the square units and realize that these 2 make 1 square unit, these 2 make 1 square unit. However they come up to it, they're going to get 32. What is key here is that some of your kids who are a little bit more quick to come up with answers are going to look at this piece here and count it either as 1 square unit, which they can't do, and that's mostly because there are no folds in there. So if they're strictly looking at the folds, they're going to say, well, this is 1 square unit, when in fact it's 4. You want to point out to them that this occupies 4 square units. The reason it doesn't have the fold is because, and again, a preview, that's going to become the top of the box. This you don't need to do, but this particular one you definitely should outline because that's going to become a guide for how we're going to slit this thing open. The other thing that I didn't get to in terms of finding the area, and we know the area is 32 square units, but those of you that work with high school kids want to talk about this particular triangle because you're going to have a kid, the younger kids, and you may not be able to explain it to them depending on what grade they're in, who are going to say, well, I know that the area of a square is the side squared, so how come everybody's getting 32 square inches when in fact if I do 1, 2, 3, 4, 4 times 4 is 16, I only get 16. Well, the point is, this is not equivalent to 1 unit anymore. Those of you who are teaching kids with geometry, if this is 1 and this is 1, using the Pythagorean theorem, we find out that this side is actually the square root of 2, which means that the area of, the length of this side is 4 rad 2. I'm going to take a piece of paper to show you the math here. So if we have a side that's equal to 4 rad 2, using the kid who brings up that idea that the area is side squared, we say that it's 4 rad 2 squared. And basic algebra tells us that this is equal to 16 times 2, which again gives us the 32 square units. So the older kids, probably beginning in 7th and 8th grade, should start to see that, yes, you could do it by counting the boxes, but you could also do it by using the geometry of the right triangle. This is an isosceles right triangle, as we said. All right, so getting past that, now we get to doing the folding. This is where I lost most of you because we were so rushed and that mean man came in to do his session when I thought nobody was coming in. So what I had said to you is tell the kids to take that square and pick 2 parallel sides of the square inside, the smaller square. I don't care if they pick the the vertical ones or the horizontal ones, but they have to pick two opposite sides of that square that's going to become the top, and extend those sides all the way to the edge of the square that we were working with. Now, I think most of us got this far. It was once we made the cut and the fold that things got ugly in our session. So you have this. Again, I'm going to remind you to tell the kids, do not pick up the scissor, because we're not using the scissors until we figure out what we're cutting. And again, using vocabulary, you could say to them, we're going to make 4 slits in this. Nothing is going to fall off. The 4 slits are going to go from the edge of the square we started with right up until the vertex of the square that's inside. That will become the top of the box. So you have 4 slits, and basically this is probably something that you're going to have to show them. I'm using a darker marker. Hopefully that'll work so you can see it better. So you have that. And again, this is in the handout. This is on your PowerPoint, where one of the slides shows exactly where they have to cut. Whoops. Again, the more accurate your cuts are, the more accurate your folds are, the better your box is going to look. So what I think I had said during the class is, if you want, you could tell the kids to shade this in so that they could keep an eye on that from underneath the box and realize that that's going to become the bottom of the top of the box, if you will, or the underside of the top of the box. So the next thing is where we make the slits. All right, so we're taking the scissors and we're simply making those 4 slits, 1, 2, 3, 4. Remember, you could write anything you want in here. Nothing's going to show once the box is completed. So I'm going to make the slits. Try to keep it down so you can see what's going on here. And once again, this becomes a great time to talk about the shapes. Remember, this is probably the 3rd day of a lesson that you're doing. So you want to show the kids that we have 2 flaps here that are congruent. Use the word congruent again. What is their shape? Hopefully you get from them that it's a pentagon. Okay, is it a regular pentagon? No, because these are 90-degree angles down here, and these certainly are bigger than 90 degrees. And again, you want to just hit them away with the vocabulary. The other 2 flaps that you have are these 2 gigantic triangles. What kind of triangles? Specifically, isosceles. It's also an isosceles right triangle. It is not an equilateral triangle, because while these 2 sides are equal, this one here is longer than those 2 sides. So yes, they are 2 isosceles triangles. They are congruent to one another, but they're not equilateral triangles. And you got to use those phrases, because that's how you're going to describe making the fold. And this is where all hell broke loose in our session. So I'm going to try to get it right now. I tell the kids to hold the baseball square with home plate towards them. Home plate being one of the pentagons. Then we're going to take the 1st and 3rd base and fold them into the centroid as we did on the original fold. The second fold, which we actually went all the way to here, we're not going all that far. We're simply going so that it's perpendicular to the desk that they're working on. You do that on both sides. Here's the tricky fold. I tell them to fold in these flaps, but as much as I tell them and several of you who tried it, they're folding in just this little triangle piece. The point is, all of the folds have to lie on the inside of the box. That's why we outlined it, so they know where they're going. So it's not just this little triangle piece, it's the whole triangle plus the square attached to it. Okay, so that one goes there. This one comes in and does the same exact thing. And then the pentagon comes up, over, and inside. And if you made your folds great, then you don't need any tape. If they didn't, and the first time they do it, a lot of times the kids will not have made such great cuts or folds. Have some Scotch tape, and you'll be able to put a piece of Scotch tape there once they do the second side of the box. They do the second side of the box. Same exact thing. You fold into 2 flaps, the square part and the little triangle. And notice how when they come together, everything is doubled in thickness. This piece is already doubled. This is doubled. Each one of these is single, but they lie on top of each other because you actually have two more isosceles triangles there. All right, and again, you bring up the flap, the pentagon, you bring it in, and you bring it down, and you have the box. That is it, folks. Turn it over, you have the box. My design makes no sense. You can do so many other things with the design. As I said, if you really want to stretch it out a little, don't color them in at all. Just give the kids boxes or diamonds or rectangles and have them color it in. Now, what we didn't get to, there's so much more to deal with here. First thing is surface area. So I say to the kids, okay, what is the area of the top of this box? Well, if they remember their units, this was 2 by 2. So the area of the top of the box is 4 square units. Then I want to talk about surface area so they can see the relationship between the linear measures, the square measures, and surface area, which is also square measures, but you have a visual here for them. So the question is, while this is 4 square units, to get the surface area of what I'm looking at, if you want, you can add in the bottom when you get the second part of the box, what's the total surface area of what I'm seeing here? Well, they have to then look at the side of the box and figure out what its area is. And hopefully they come up with the fact that this is 2 units by 1 unit, so this is 2 square units. This is 2 square units. So around the edge of the box, we have 4 times 2 square units, which is 8 square units, plus this 4. We have a total surface area of 12 square units. It's a great thing to do. If you want to play the game that there's a bottom on here, then we have to add in another 4, and the surface area is 16 square units. Now, you could go one step beyond the square units and the surface area and play with volume. So something that I thought of while I was doing this the first time is I took one of these pieces of paper like this. I really feel like an idiot that once again I can't come up with this name. But I used something that we're going to talk about in a minute to figure out how I would make these boxes be perfect centimeters. And it turns out that I had 1, 2, 3, 4, 5, 6. So I have a box here that's 6 centimeters by 6 centimeters. Or if you want, 6 units by 6 units. So once again now, you could talk about surface area. This is 36. This is 1, 2, 3, 4, 5, 6 times 3. Each one of these is 18. You have 4 18s, which is 72, plus 36 is 108. And then you have another 36 down here, although I don't have lines on it, and I'll show you why I have the lines on it in a second. So you have a surface area of 144 square units on this, because I chose to make my square units smaller. And this is a great way for them to see ratios and proportions also. But more importantly, I did this because now I wanted to talk about volume. So I say to the kids, all right, what's the volume of this? You could go back to this one also. Let's do it, as a matter of fact. The volume of this box, let's say it's an open box, and I say to them, how much does that hold? They need to know that the length times the width times the height. So it's 2 by 2 by 1, which means that the volume of this thing is 4 cubic centimeters. Well, I'm sorry, 4 cubic units, not centimeters. This one, with the centimeters, is 6 by 6 by 3. So this is 108. 6 times 6 is 36, times 3 is 108 cubic centimeters. What's great about this, and why I did this was, if I could open this up, I think I showed some of you this that hung around. I took those little centimeter cubes that all grade schools have, and they actually have a visual for 108 cubic centimeters. They could take these out and count them up and realize that once we did the formula, there should be 108 of those guys sitting in there. And indeed there are. Well, not mine, because I've already lost some, you know. You figured out by now that I'm not the neatest person on the face of the earth. But here's a great visual again for showing them about volume. Put that aside for a second. The only other thing that we didn't get to, or that we talked about a little, was the size of the box as it relates to what we started with. So what we came up with, and again, you're going to have to look at the last page of your handout, I believe it was, where I talk about the ratio of the side of the, let's see if I could reproduce it here. We said that the square that we started with had a side that was 4 times the square root of 2. But then we said that, so this is the original square, I'm writing sideways here. The finished product, the top of the square, let's go back to this guy, had an area of 4. Take that back. Had a side, rather, of 2. We're doing with sides. So the side of the original to the side of the finished product. If you change this into a reduced form, you get that it's rad 2 over 1. So for every inch or every unit of the finished box, we need this much for the original box. Now this happens to be equal to 2 times the square root of 2 is 1.414. It's an irrational number, but it's close enough to 3 that we could say it's really 2.828 to 1, which simply means that if I want a box of a certain size, I have to start off with the square that's 3 times, a little bit less than 3 times, but as I said to you there, when I did a little bit less than 3 times, because of the thickness of the paper, forget about the decimals and just do a ratio of 3 to 1. So I think the question that I had asked during the session was, well, let's say I wanted to make a 10-inch pizza box. And I only use a pizza box because it's a square box. So if the kids wanted to make a 10-inch pizza box, they would have to start off with a piece of paper or a piece of cardboard that was 30 inches on each side, because we're going to lose 2/3 of that box. If you remember, this thing started at 4 rad 2 square units, which was about 3 inches on each side, and it turned into something that was, may have been 6 on each side, and it turned into something that's 2 on each side. So those are the things that I wanted to get to. I did not get to them as well as I wanted to. I don't know that this is too rushed, but at least you have something to look at, especially the folding that took place. Feel free to call me or email me if you have any questions. Again, my email address is nrestivo@moems.org. If you feel like talking to me, it's 516-781-2400. And I hope this helped. Again, I apologize for everything that went wrong with that particular session, but I hope this makes it better, and I hope this comes out as well as I think it did. Take care, everyone. Have a happy Thanksgiving and a wonderful holiday season.